Hello, everybody. Thank you for being here. My name is Omar Guerra. I am research engineer at the Grid Planning and Analysis Center, or GPAC, at the National Renewable Energy Laboratory. And today I'm going to be presenting a global perspective on low-carbon hydrogen. So, the first question that we need to ask is, why hydrogen? Why are we talking about hydrogen, right? So, in order to avoid catastrophic consequences of climate change, we need to do a transition of our global energy system towards net zero emissions by 2050. And that means that we need to decarbonize not only the electricity sector, but also the industrial, transportation, and building sector. And hydrogen could play a key role in this transition. For example, hydrogen could be used for power generation in the electricity sector and, use renewables for seasonal storage. That means basically, use wind and solar PV surplus during spring and summer to produce hydrogen. Then we store that hydrogen for 4 or 6 months. And in winter, when you don't have enough wind and solar PV power generation in the system, you could use that hydrogen in a fuel cell or gas combustion, hydrogen combustion turbine to produce power. In addition to that, we may use hydrogen for the production of ammonia. This is in the industrial sector. We may also use hydrogen, for example, for aviation, shipping, or heavy-duty vehicles in the transportation sector. So in summary, hydrogen could play a key role in this energy transition. And hydrogen indeed could help us to decarbonize not only the electricity sector, but also the industrial and transportation sectors. Now, in this diagram, you can see the projected hydrogen demand from the International Energy Agency. And this is associated with the net zero by 2050 global energy system scenario. And I would like to mention 3 key aspects here. First, the demand is projected to increase from less than 100 million tons per year in 2020 to more than 500 million tons per year by 2050. In addition to that, as you move from 2020 to 2050, you see that there are more colors in these vertical bars. And that means that, the demand for hydrogen is going to be more diverse, right? So that means, new applications, for example, hydrogen blending with natural gas, seasonal storage, hydrogen for aviation, for shipping, etc. And finally, if we want to use hydrogen for the energy transition, we need to decarbonize hydrogen production. That means that we need to move from the current technology that is steam methane reforming without carbon capture and sequestration towards more clean hydrogen production pathways, including, for example, renewable-driven water electrolysis, biomass gasification or pyrolysis, or steam methane reforming with carbon capture and sequestration. Regarding near-term opportunities, today we use hydrogen for refinery and ammonia production, for example, and those are near-term opportunities, right? Like we could just start to decarbonize existing hydrogen uses, specifically ammonia and refineries. Now, let me talk a little bit about how to evaluate a given hydrogen production pathway. And here I would like to mention 2 key metrics. The first metric is the carbon intensity. That is basically, how much CO2 is produced per each kilogram of hydrogen that we produce. For example, for the technology that we use today, actually in the US, the steam methane reforming produce around 95% of the total hydrogen production. And this technology has a significantly higher carbon intensity. We are talking here about between 10 and 15 kilograms of CO2 per kilogram of hydrogen. In addition to that, as we move to, let's say, more kind of electrolysis system, water electrolysis driven by renewables, then we have, carbon intensities around maybe 0.4, 0.5 kilograms of CO2 per kilogram of hydrogen. So this metric is important. Indeed, in the US, we have an incentive that is called production tax credit, and you could monetize this credit depending on your carbon emissions. For example, if you are above 4 kilograms of hydrogen per kilogram, sorry, 4 kilograms of CO2 per kilogram of hydrogen, if you have, a carbon intensity that is higher than that level, you are not able to get any incentive. But if you are below that threshold, again, 4 kilograms of CO2 per kilogram of hydrogen, you may be able to get incentive from, $0.5 per kilogram to $3 per kilograms if you are below 0.4 kilograms of CO2 per kilogram of hydrogen. So this metric is very important. In addition to that, of course, the production cost is a key metric, right? So on the right, you have the projected hydrogen production cost and also the current hydrogen production cost for different pathways. For example, today we may be able to produce electrolytic hydrogen driven by renewables or nuclear at $3.6 per kilogram, but there is a variation there, right? Like the production cost depends on where you produce that hydrogen. But when we move, as we move to 2030, we may be able to reduce that production cost by almost 50%. And this is, significant cost reduction. So we may be able to produce electrolytic hydrogen driven by renewables and nuclear at $1.6 per kilogram. And this is without the incentive that I was mentioning before, that is called production tax credit or PTC. In addition to that, if you take a close look at the composition of the hydrogen production cost, you can see, that the driver is the operating cost. Regardless of the technology, the operating cost represents more than 50% of the total hydrogen production cost. So, if we want to reduce hydrogen production cost, the focus should be on reducing the OPEX. And, the OPEX is associated with the primary energy source that we use to produce hydrogen. It could be natural gas, could be, renewable power, could be nuclear power, for example. Now, let me talk a little bit about the US context, right? Like, where is the hydrogen industry in the US going? So here you can see a summary of the existing hydrogen projects in the US, and most of them are focusing on, ammonia production of synthetic fuels and biofuels, and also refinery operations. So, those are the near-term opportunities. So the near-term opportunities are basically, the decarbonization of the existing hydrogen uses, including ammonia and refineries. Now, let me talk a little bit about the global context. And here on the left, you can see, the timeline with, the information regarding when the renewable hydrogen production could be cheaper than blue hydrogen production. Blue hydrogen production is the production of hydrogen via steam methane reforming with carbon capture and sequestration. And green hydrogen is basically renewable hydrogen that is produced either via, water electrolysis driven by renewables or nuclear, or electrolysis driven, for example, or hydrogen production driven by biomass gasification or pyrolysis. For India, right, by 2025, this is, 1.5 years from now, you may be able to produce renewable hydrogen, either, from biomass or via electrolysis with renewables at a production cost that is going to be lower than the cost to produce hydrogen via steam methane reforming with carbon capture and sequestration. So there are significant opportunities in the near term to produce renewable hydrogen in India. If we move to the right, you can see, a summary of the existing international projects for importing and exporting hydrogen. And, regarding importing opportunities, those opportunities are going to be mostly concentrated in Europe and also Pacific Asia, Japan and South Korea. And then exporting opportunities are going to be mostly located in, Latin America, Chile, Argentina, Brazil, North Africa, and also Australia. Now, let me talk a little bit more about those specific projects. So here you have, the name of the project, the export country, import country, the volume that is going to be imported or exported, and also the carrier. And I would like to call your attention here, because if you check this column, carrier, you see a diversity of carriers that are used to transport the hydrogen for the exporting country to the importing country. And this is because, each project is different, right? So there is no, unique solution for the transportation and storage of hydrogen. Hydrogen is a very, low density energy carrier that is very expensive to store and transport. So these costs need to be minimized for those international projects. So for example, if you are, let's say, importing hydrogen from Australia to Japan to produce ammonia in Japan, it is better to produce ammonia in Australia and then transport that ammonia that has a higher energy density, so less storage and transportation costs, and then use that ammonia directly in Japan. So the selection of the energy carrier is key for those international projects. Now, if we want to develop a global hydrogen market, there is a need to develop a global certification scheme because each player in this international hydrogen market needs to play the same rules. So this is very important. So for example, on the right, you can see a quick summary of what is called a hydrogen passport, with information regarding, what are the carbon intensity of that hydrogen, the water footprint, the land use, and also the waste management, some information regarding the safety standards and codes. And this is important because everybody in this international hydrogen market needs to play the same rules or need to play under the same rules or regulations or conditions. So this is very important. And with this, I would like to conclude this presentation. Thank you very much for your attention. Here you can see my email. So if you have any comment, any question, please feel free to send me an email, and I will be more than happy to answer to any question that you may have. Thank you very much.